Hello, organic chemistry. I am so excited. I love E2 reactions, and that's our next series of videos. Now, we are right smack in the middle of Unit 3. So if you're watching this video first, let's pause for a second. You want to watch radical halogenation. Those are already posted. And then you want to take a look at our SN2 and then watch this video. So if you haven't seen the SN2 first, then definitely stop this video and watch the SN2 video first. That one is gonna go, we're gonna complement, and I'm gonna refer back to the SN2 quite often in this video, so you definitely wanna watch that one first. All right, I love it. Okay, so this is one of my favorites. This one's going to be a little bit bigger, so we're going to have maybe a couple videos for this one, not just one video, but it's such an important reaction, and the stuff that we're learning today for this reaction, we're going to use for the rest of the semester. A lot of this vocab and a lot of these concepts we're going to see, in fact, all the way through OChem 2. We're going to talk about I actually want to start all the way back at an SN2 reaction, and then we're going to just get deeper from there. So you'll notice that I kept a lot of the links that were in our SN2 video because they're relevant for this one also. So I kept those, and then I added some new ones. And there is maybe one more I wanted to put in here. It's that Mastering Organic Chemistry. They seem to have a good, just quick and dirty way of looking at some of this. So let's write that Master Organic Chemistry. There is a video that is comparing nucleophiles and bases. So that is also a good one to take a look at. And that's what we're going to do in this video. So I am so excited. Let's go all the way back to the beginning of our SN2, and let me write out that very first reaction, and let's do some vocab. It's like a little mini warm-up. So grab your yoga pants and just get zen. This is a nice warm-up right before we get a little bit deeper. All right, that very first reaction we looked at for an SN2, we took sodium hydroxide and we reacted with either methyl chloride or methyl bromide. In our case, we had methyl chloride. And we looked at our mechanism. Remember, for the rest of this semester, we're going to start our new reactions always with our mechanism. And we noticed that we had available electrons here. And what did available electrons tell us? I mean, it was so glaring with that negative sign that we have available electrons. We saw available electrons first in our last unit as a base, and then we saw available electrons again in the SN2 as a nucleophile. Well, what today's video is about is, holy crap, which one is which? So if they both have available electrons, and in both an SN2 and today's reaction in E2, they are negatively charged, so you can spot them right away. So how do you know if you have a base or a nucleophile, or why do you care? Are they the same or are they different? We'll see today that they are actually different. There's a set of rules for both of them. In fact, they compete. Ooh, nothing like a little healthy competition in your OChem class. There we go. All right, so let's draw this SN2 mechanism. We go from where we have available electrons to where we don't. So we saw over here a nice partial positive, a real positive, or in the case of our Lewis, available space. So right here, we had our easiest bond to break. We had a partial positive on that carbon, and we spotted, let's put in our vocab. I feel a color code moment coming on. We spotted over here the fact that this chlorine would make a good leaving group. And that's how we could also tell right here that nice partial positive on that carbon. So naturally, if you have extra electrons, they're going to go to where you don't. So let's draw that mechanism. And we ended up literally substituting that chlorine with that OH. So our SN2, this is the first part. This is a substitution. That's the S in your SN2. And we substituted with our nucleophile. Okay, our nucleophile was right here. So that is your N. And then our 2 was a collision. And you'll notice our reaction today is a 2 also. So that's a pretty good guess that that's going to be a collision. Okay, now what made this a nucleophile? Look at the bond we formed right here. That bond was to carbon. Okay, that bond to carbon means this was a nucleophile. If that bond had been to a hydrogen, it would be a base. That is our only difference. What are your available electrons bonding to? Okay, I love it. So then what was our other byproduct we had to leave behind? Our leaving group. We leave behind those electrons. Oh, that was a little too fluffy there. Let's leave behind that. There you go. Okay, so here's what's awesome. Let's get a little bit deeper. We learned with our SN2 that there were 4 major components that we will always look at. Let's spell them out and let's make sure we know what is what. That first one was our nucleophile or our base. Okay, we found that. We also have a list of those. Okay, we have something called an electrophile. Electrophiles are kind of like acids. Check it out. Our available space over here was our electrophile. We had a leaving group. These are always connected. You can always spot your electrophile by your leaving group. Our leaving groups for us this semester will specifically be a chlorine or a bromine, but they could be anything that is a good conjugate base to a strong acid. And then number 4, we had solvent. So let's make this a true SN2. Let's put this in a nice polar aprotic solvent like DMF. And then let's also mark one last piece of information, our electrophile. And I'm going to train you to add to that it is primary. Okay, we don't count the bond to chlorine. You don't have another bond to another carbon, so that is a primary carbon. You have bonds to 3 hydrogens there. That is on the outside. So if our SN2 then is a collision, we talked about in our last video that collision has to happen at a very specific angle. In fact, we called that a backside attack. I know I didn't make it up. And that inverted our stereochemistry. So if you have a stereo center, you just inverted any stereo center. So why do we care about any of this? Aha! Because we saw that our primary electrophiles reacted much faster than our secondary electrophiles. And in fact, our tertiary electrophiles never reacted in an SN2. So if we were to get just a little bit deeper with our SN2, we would say this is actually pretty fast, and this one is slower. Because of that collision and that backside attack, you have to have just the right angle. Well, when you start comparing a primary leaving group and a primary electrophile to a secondary, right here you have a nice free path to your backside attack, and now you're getting stuff in the way. In fact, think of those methyl groups and there's hydrogens there. Now you're getting steric hindrance. So that's exactly where we're going to start today, is this idea of steric hindrance with our SN2. So let's compare. So if I were to take and get just a little bit sassier with that above reaction, use the same sodium hydroxide, could we predict, and I'm just going to go ahead and add a solvent. Why don't I go ahead and say acetonitrile for this one? All right, what are we going to make? Well, we learned in our last video, start here, leaving group. Your leaving group is attached to your electrophile. Okay, your hydroxide would be your nucleophile, and you have your solvent right there. So let's draw that mechanism. What are we going to make? Let me go from our available electrons, backside attack, right there. And now we just made a propanol. I need to have that color coded. There we go. We just made that bond. And we're going to leave behind sodium chloride. You're thinking, okay, chill, Dr. Morty, stop repeating. I've already got this. Okay, well, this is a nice primary electrophile right there. And that reaction works really well. And in fact, we can use all kinds of nucleophiles here. So in fact, when we look at our list that we used in our SN2 video, but then we didn't really comment yet, when we look at our list down here, check it out. We've got good nucleophiles and then we've got strong bases. Why is this list different? Well, when we have a primary electrophile, like we just had, so primary right there, this list is all the same. These are all nucleophiles. Okay, now something magical happens though. Wait for it. It's like a cliffhanger. If you need to pause and get a snack, this is going to be good. Okay, wait for it. What happens then when I switch to this? Now we have a nice secondary. Let's keep the reaction the same. You're headed to the lab. You're super excited. You've got this down pat, and you're like, done, I'm about to make rubbing alcohol. And I'm going to make millions from it because I'm sure no one has done this before. So let's do it. All right, so in your mind, you know, okay, it's secondary, but I know that so here's my leaving group. Here's the electrophile. This time it's secondary. So we know that that reaction can still happen. Here is where it's different. This reaction up here is easy for that collision. This is a fast reaction. Okay, now it's a little bit slow. Slow is when competition happens. Oh, the plot thickens. All right, so now we're going to start to have a competition. So let's draw what you feel like we're going to make. Okay, watch this. In your heart, you're thinking, Dr. Morty, please challenge me. I'm about to make rubbing alcohol. So this is what you feel like. Okay, done. I'm going to make that plus sodium chloride. Okay, I've got it. Only, in fact, so maybe this is what you feel like you're going to make in theory. Only, in fact, son of a motherless goat, when you actually do this reaction, what you make is something entirely different. Okay, so the first time this reaction was done, I'm sure this was a shocker. Well, wait a second. Why did you actually make this? And what in the heck is it versus that SN2? Well, this is where competition happens. So let's get deep. In this case, your sodium hydroxide, you were hoping would act as a nucleophile. That would be your product from an SN2. This reaction is a collision. In reality, you're going to make an alkene. So do you notice that the OH does not end up in that product? So that means it is not a substitution. In fact, this is called an elimination. Because not only do you not have the OH in there, you also don't have your leaving group. Okay, so let's draw the mechanism for what happens, and then we're going to get deep in our competition. So what is happening here, let's redraw our compound, but for some reason my pen just stopped on me. I think it's because I'm on a new page. Let's see if I can get that to work. Hang on, I got to plug in my pen for a second while I'm talking. Okay, so if we've got a nice competition happening, what does that mean? And how do you actually make an alkene using that base instead of your nucleophile? And what is really happening? All right, so let's try this again. And my pen just quit on me. Let's see if I can get it to recognize. We may have to stop our video if I don't have my pen working.